In the previous video, we talked about how to implement the hash table, or we say hash map. But one member function you can see, the load factor, we didn't really talk about that much. So let's talk about this load factor. What does this one mean? No matter we do the chaining implementation or probing implementation, so here is linear probing implementation. So you will see here we use the array size is capacity. So each array element is a node. So we have the load factor. I just have the inline function to have that is the percentage, actually is the decimal for the total used element size divided by the cap. So that's what we call the load factor. The same thing for the chaining implementation. Chaining, even we still have the node struct, but for the array, we have the array, each element data type is a list of the node. So even here, by definition, the load factor still is the size divided by cap. The size means how many nodes so far, then divide by the cap. So that's what we call the load factor. That's the definition for the load factor. So here we say, one thing is when we do the hash table or hash map, the best way to help us to improve the runtime is because we have the key. We're using the hash code function to convert the key become index. Because we have this index in the array, so that's why we can have our runtime to be the search time is the big O 1. So that's the reason we improve our runtime. But the improvement load factor is affect a lot. Did you remember we talked about before? If I have Joe as a key, or I have the name is Geo. Actually, they have the same key. They have different key, but their index value will be the same. So that's why in the linear probing, we have the collision. So we need to find the next available not in use the node to save the geo. So that's why here why we need the load factor. Is the load factor really affect our hash table runtime? If the load factor is too high, we will create a lot of collision. Like here, even I have the Joe already, but Geo, when they try to find the next available node, they maybe need to go over a lot of comparison if our load factor is too high. So that's why here we have the suggest the load factor for different implementation. For the linear probing, the load factor at the most only can be 50%. Even the 50%, actually that means have chance you will have the collision. So sometimes if your node is too crowded, they have too many collision, they will affect our runtime. So we see, for example, when we have the geo, we want to find the next available node. I just show you here, for example, O if I mark as the black in the number, that means they're already being used. So that's why you see the geo, when they come to this node, they will see, oh, that's being used. So that's why I need to find the next available one. So that's why you see here, if that's here is not so crowded, so the next one is not in use. Also, then the following one being not in use. So then I can put the geo here. But sometimes if our node is really crowded, so that means all the time they will have the collision. So that's why here when you have collision more, you will affect your runtime. sometimes if they're too crowded, you will maybe from your big O1, your runtime will go to the big ON. So that's the load factor for. So the load factor for the linear probing, they should be 50%. So then for chaining, they can be much better. Because one thing is, for chaining is, chaining. So when we talk about chaining actually, after you find the hit is 86, right? You are not only finished. Actually, after we hit this match index, for chaining each element, there will be a node list. So my geo can just add to the end. So they just need to go over, see how many, so then they will add to the end. So that's why chaining, we can allow a higher load factor. But one thing is, even chaining is 80% for the load factor, we are acceptable. But one thing you can see, because chaining actually, you will have each node, each element, they are the list. So maybe here, even I count 1 node, 2 node. So for geo and Joe, they both need to be increment the size. But when we do the size to divide, we still divide the cap. So do you understand what I mean? So supposedly when we do the size, when we do the capacity, we want to do the load factor. The load factor actually is equal to 1.0 times size minus cap. So this one for linear probing is fine because that definition is good. Because linear probing size really means how many index being occupied in the linear probing. So I can divide by the cap. But when we're using for the chaining the size is not only mean how many elements being occupied. Because sometimes even this index, we have the list we have node in the list, but sometimes this list can be 2, can be 3, even can be 10. So that's why here your size is not really show how crowded our array is. So that's why here I want to suggest you for the chaining implementation, our load factor we need to change for a little bit. So here, actually for your homework assignment, if you want to use the chaining implementation, I will give you one more load factor. So this load factor we still have is the size divided by cap. We don't change. But actually, we need to add another load factor. That's I call node load factor. So this node load factor mean is how many nodes really in there. So on the other hand, we need to be careful. So here, when I say the size, it doesn't mean how many nodes. The size just means how many elements in the array they have not empty list. If any element in the array, your list is not empty, so we need to increment the size. So here, n underscore node is really mean total how many nodes. So that's why here, after you have this one, we can have, after we have the load node, is really see how busy it in the array. But the node load factor, we will really use the total node size divided by cap. So at the end, if we try to use the node load factor divided by load factor, they will give us the average size of the node in a list. And that one is really the runtime, average runtime for the chaining implementation. So after we have this node load factor being defined, so this one actually the new defined chaining interfaces will affect our square bracket setter function and the delete key setter function. Because every time when we add a new node, we need to check if the list is empty. So then the size need to increment. So then whenever I add a node into the list, I need to increment the n_size. The same thing for the delete key. Whenever I have a node delete, I decrement my n size. But after I delete that node, we also need to check if the list become empty. If the list become empty, the size need to decrement. So that's the updated public interface after we have the node LoadFactor added into the training implementation. So that also will affect our square bracket setter function implementation. So when we try to add a new key, we still need to get the desired index. So after we find the index, we still need to use the iterator to go over our list. But one thing is, after we add the node, we need to be careful. Before we add a node, we need to check if this list is empty. So then you see here we have a new node we need to increment. So that's why here they need to increment the size. So then whenever we have a new node, we will add increment. We don't add the size, actually we add the n size. So that's the change. So the same thing for our delete key function. So the delete key function, the same thing after we have the new n node. So then when we try to find the index, still the same. When we try to use the iterator, go over the key, still the same. So whenever you have an array, so you find the key, you try to erase that node. So this one still the same. But here, when you delete, when you try to decrement your size, actually you decrement your n size. So then again, the same thing. After you see you've completely deleted that key, we need to check if our list is empty. Because if this list is empty now, we need to decrement the size. So that's updated the training implementation. And also that's why the LoadFactor is important. They will affect our searching time runtime.